So hello again. So we will start then with the first tutorial of the day. And the tutorial is about chiral quantum optics, and it will be presented by Professor Peter Lodahl. Peter is a professor of quantum physics and technology of the Niels Institute and director of the Danish National Research Foundation Center of Excellence in Hybrid Quantum Networks. And his groups develops fundamental new quantum hardware for the emerging field of quantum information science, and such as deterministic single-photon sources, single-photon interfaces, and photon quantum gates. Note that during the talk, you can ask questions in two ways. One of them is by raising your hand by clicking the bottom at the bottom of the screen, the icon, or by directly typing in the questions with the Q&A icon that you have also in the bottom. And then you need to wait to Peter to give you the word for him to either read the question or let us give you the microphone so you ask the question yourself. Now, I noticed that there are many of you already connected in YouTube. Take into account that we will not be able to interact with you. Try to, if you want to make a question and interact with the speaker, please make sure to connect with Zoom. So with this, I give the word to Peter, and I'll let you share your screen. Thank you, and welcome to the conference.
Thank you very much, Sergio. You can hear me?
Yes.
Perfect. So thank you very much for the very kind introduction and the opportunity to speak. I will share my screen. See the right one now? Yes, I think so. Yeah. So let me just get the pointer also. Just a second. Yes, and I think we all set. Yeah, thank you very much, Sergio. It's a real pleasure to give an introduction to the area of photonics, and in particular also the quantum properties of light matter interaction, and introduce the concept that we call chiral quantum optics. So this is really about directional emission and directional light matter interaction. It may be topological or it may be not topological. I'll return to that later. So what we're really in particular interested in is the ability to engineer light matter interaction and play tricks with light transport and light emission. I'm headed here at the Niels Bohr Institute at University of Copenhagen, and here you see some of the founders, and indeed Totja that Sergio introduced. We are very happy to be part of that very nice and interdisciplinary project. So this is the outline of what I will be speaking about. I will introduce chiral light matter interaction. I'll introduce the notion of a transverse photon spin. And then I will explain in more details how that gives rise to directional photon emission, and single photon emission in particular, and also that this can be deterministic. And this is really the key of what we can do also for to build technology based on this, that you can really get single emitters interacting with single photons near deterministically. I'll say something about the applications that can be foreseen. I will explain about how we can make non-reciprocal photon transport, so we can route photons so that there's a difference between backwards and forward, and we can do it with quantum interaction. So that means we can also do it in quantum superpositions. I'll say a little bit about some of the applications in quantum information processing that are foreseen. Probably I'll not go too deep into these details about how we can make quantum gates and multi-photon entangled state based on some of these concepts. And I'll also touch briefly upon nonlinear properties of this light matter interface and how the nonlinearity can operate at the single photon level. And please, as Sergio already said, please just raise your hand and ask questions as we go along. That will make it easier for me to adapt to the audience. So, light transport and the longitudinal electric field and the transverse photon spin. So in optics, we are used to, we have beams that are propagating. Here you see a Gaussian beam that can propagate along the plus z direction or along the minus z direction, just for simplicity. So that's a Gaussian beam that propagates. We're used to think of photons as, or light as being transversely polarized. So you'll have a propagation direction here that is in the plus z direction, and then you'll have the electric field pointing in the transverse direction, either in the x or the y direction, or it could be a circular polarization, a combination of x and y. However, this is an approximation actually, because we know from Maxwell's equations, the divergence of the electric field has to be equal to 0 in free space. And that actually means that you have a, so dEx dx plus dEy dy plus dEz dz is equal to 0. That actually gives a longitudinal component of the field, a component along the z direction. So that's just from divergence of E being equal to 0. I get a longitudinal component that is equal to this expression here. And normally, or often, we can neglect this contribution because this is really small unless I have a transverse variation of the electric field dEx dx, dEy dy, that is significant on the length scale that is, well, there's a wave number here. That's the wave number that is 2 pi divided by lambda. So that's the length scale here. So if I have a transverse variation of the electric field on the order of the wavelengths, then I actually get a longitudinal component of the electric field as well. Often this is we can neglect that. But in the nanostructures that I'll be introducing here, we are starting to confine light to a length scale, to a spatial transverse length scale here on the order of the wavelengths. And then we cannot neglect this longitudinal component of the electric field anymore. And the electric field is not fully transverse. I get a longitudinal component. Okay. Another thing we need to understand is that, well, moving forward along this plus z direction and moving backward along the minus z direction, well, the electric field is a complex conjugate of each other. That's reciprocity of Maxwell's equations. It's not that I'll have electric field moving forward and nothing moving in the backward direction. That's not allowed by reciprocity, but I have a complex conjugation there. So that means the longitudinal component of the field moving in the minus z direction gets a sign change compared to the longitudinal component moving in the forward direction. You also see there's an imaginary unit here, so it's out of phase with the transverse components Ex and Ey. Okay, so this is something that we are usually or often just neglecting in optics. We're assuming the field to be transversely confined or transversely polarized, sorry, which is perfectly fine in many cases where we don't confine light to these wavelength length scales. But that's exactly what we do in the photonic nanostructures, as we will be talking about today. So therefore, this longitudinal component comes into play. That also means that if I calculate the spin of the field, of the light field, and spin of the photons, so you see the mathematical expression given here, well, then if I have transverse, like linear polarization, for instance here, then I'll have a spin pointing along the propagation direction. But now I start to have an electric field, sorry, pointed along the propagation direction. That means I get a transverse component of the spin as well. And that you see illustrated here and calculated for a very simple structure. So this is just an optical fiber. You see optical fiber from the top essentially. So, but it's a fiber that is tapered to a length scale that is comparable to the wavelength. So a few hundred nanometers or 500 nanometers would be a typical length scale in photonics. And you see, if I calculate the polarization, well, then it depends on where I am spatially. Here you see Z is a propagation direction, X is a transverse direction. If you're here in the center of the fiber, well, then the polarization is primarily linear. You have a linear transverse polarization. But as you start to go closer and closer to the rim of the fiber, which is right here, then you start to get a more and more sizable longitudinal component, the one I introduced before, and you actually can get almost circular polarization here at the rim of the fiber. So you get a transverse variation of the polarization. If I equate the spin, then it means, as I explained over here, you also get a transverse component of the spin. So here you see this transverse component of the spin now in the y-x plane. So this is a cut through the fiber. And you see here next to or close to the rim, you start to get a sizable transverse spin component, and it changes sign going between plus x and minus x. Okay, so that was the basics of this longitudinal component of the electric field and the transverse photon spin. So there's a nice review paper written a few years ago by the group of Gerd Leukes, who's introducing these the transverse spin and the longitudinal electric field, and speaking about illustrating it with these illustrations here, saying that the the transverse polarization that we are used to, that's like this propeller field here, where the electric field is rotating transversely in the plane. That gives you a longitudinal spin component. But there's another opportunity that would be like a bicycle wheel that rotates in the other directions, that gives a transverse longitudinal spin component, and a longitudinal electric field component would be the electric field analog of that. Okay, so since we're doing quantum optics, we're very much interested in what are the quantum optics applications or implications of this longitudinal electric field. And then we have to go back to our textbook, Quantum Optics. What is the essence of quantum optics? That is, how does light and matter interact with each other? The first thing that we say every time we give the quantum optics lecture is that, well, you have to remember that light matter interaction, the interaction Hamiltonian, is the dipole moment of the emitter that I place, that I want to interact photons with, projected onto the electric field. So it's d dot E. So d dot E, an absolute square of that would be the decay rate at which this quantum emitter, quantum dot, an atom, your favorite emitter, emits light into a photonic waveguide, for instance, as illustrated here. So d dot E. And now we have the setting. Now let's look at a planar setting where I'll have a dipole moment, transition dipole moment in the plane in the xz direction. Z is a propagation direction, just like before. And in these structures now, the new thing is we have this longitudinal electric field component. I have not just a transverse component in the x direction, I also have a longitudinal component along the propagation direction here. And I can ask myself, if I take an emitter with a transition dipole moment, in the general case, it would be a complex a dipole moment. A circular polarized transition would be, well, d minus id. Here I've just written it as a very general case of any polarized emitter, and I can say, what's the probability for this to decay? Well, that would be d dot E. What's the rate at which it's decayed? That's d dot E absolute squared. And now you can see in these nanostructures, we can start to engineer this longitudinal field component. I'll introduce the nanostructures just in a second, but imagine that I can now totally engineer the local field. Then I think you can imagine that for a certain dipole that I pick, a certain atom I pick, I put into the nanostructure, I could engineer the electric field and the longitudinal component in particular, so that this inner product between D and E is optimum. D dot E is as large as it gets. The electric field is matching the transition dipole moment in the structure. So D dot E would be large, say, for a certain direction. So let's say for the plus direction, moving in the plus direction. But then, due to reciprocity that I introduced before, if E in going in the plus direction is a complex conjugate going in the minus direction, so you see, if I've engineered the electric field to be optimally oriented with a circular in-plane polarized emitter for a forward direction, D dot E would be large. Then D dot E could be zero in going in the opposite direction, simply because of the complex conjugation that I have here. And that's a fundamental principle behind this directional photon emission. I could have D dot E for a sigma minus polarized transition being very large, so that it wants to emit photons to the left here, but it would not emit to the right. And reciprocity, if I take sigma plus polarized transition, I complex conjugate D here, then that would emit to the right and not to the left. So that's what we call chiral light matter interaction. That's chiral photon emission. That the chirality of the interaction here really determines the directionality of the emission. That's a fundamental principle. And let me now introduce some of the nanostructures. So we are working on a variety of different nanostructures, in particular photonic crystal waveguides. So photonic crystals are are like semiconductors for light. So we have a periodic arrangement of holes etched into a semiconductor material, and the length scale here is about a few hundred nanometers, matching the wavelengths of the light propagating the structures. You get Bragg diffraction, band gaps, and band structures engineering in these systems. The nice thing in photonics is really that we can, I mean, the length scale, the wavelengths is relatively long, so it's these few hundred nanometers as opposed to electrons having much shorter wavelengths. So we can actually really engineer these photonic nanostructures to match the wavelengths, and we can even do engineering within one unit cell of the photonic crystal. So we can also engineer this local electric field and the longitudinal component of the electric field that I was speaking about. And that's really the game that we are playing in photonics, engineering even within one unit cell of the photonic crystal, the local light matter interaction. So that's photonic crystal structures, and we are placing quantum dots inside these structures. So quantum dots are like artificial atoms. They consist of many atoms, but they have optical properties just like single atoms and emit single photons at a time. There's another experimental platform that is pursued by particularly atomic physics groups that take tapered fibers, like I was showing the calculation for the tapered fiber in the beginning, where we also saw that you have a circular polarization, close to circular polarization, close to the rim of the tapered fiber. And for instance, Arno Rauschenbeutel's group, they are trapping atoms in the vicinity of this tapered fiber, and can also get this directional coupling due to the strong longitudinal component of the electric field in the vicinity of the rim. So that's using evanescent coupling or evanescent tail of modes, whispering gallery mode, for instance, propagating along the rim of a nanofiber here. So a few more details about the. I'm not sure I'm seeing if there are questions, so I'm not sure I'm seeing this for some reason, but you just interrupt me, maybe Sergio, if there's something that pops up. Okay, so quantum dots, a few words about quantum dots, introducing quantum dots. As I said already, they are solid state atoms, artificial atoms. They consist of really many atoms, but so tens of thousands of atoms. But they have optical properties like single atoms. I can excite an electron from the valence band to the conduction band that leaves behind a hole, and that electron-hole pair recombines, emitting a photon, and that's a brilliant single photon source, with the advantage that it's solid and it's embedded in solid structures, and I can easily do experiments on them. I can also do more advanced things like introducing a spin in the quantum dot and start to do spin physics. So here you see the nanostructures that we in particular are working on. This is a membrane structure, a 2D membrane structure. It consists of gallium arsenide, where we are etching holes into the structure. So it's e-beam lithography, enables you to write the structures and reactively etch holes in a very controlled way in these structures. It's 150 nanometers thin, so there's air underneath, there's air on top. That's very important actually to get 3D confinement of light, even though it's a two-dimensional photonic crystal structure. You have a band gap here that prevents light from propagating into the bulk of the photonic crystal. And then we leave out a row of holes here, and that's a waveguide along which we can emit photons with very high efficiency. And we are particularly here in this talk interested in now start to engineer this light matter interaction by moving maybe locally holes a little bit around here so that you can engineer this longitudinal component of the electric field. And now I see there's a question, so let me just see. Oh, it just says no questions yet. Okay, thank you. So let's see. Okay, so what are the figures of merit in quantum optics? Well, one important figure of merit is what we call the beta factor, and that is once I have the quantum dot in this photonic waveguide nanostructure, what's the probability that every time I excite it, it actually emits a photon into a single propagating mode in the waveguide, as opposed to leaking elsewhere, leaking in the third dimension out of structure, or maybe getting lost in other ways. That is a mathematical expression given here. I measure it by measuring what's the decay rate of the quantum dot into the waveguide, as opposed to the total decay rate that the quantum dot could couple also to non-guided modes, or there could be non-radiative recombination also in the quantum dot, meaning that the quantum efficiency was not very high. These numbers can be really high. So we have put an experimental lower bound on the beta factor of 98.4. And that is obviously the figure of merit of a single photon source, because that's what I've drawn here. That's a source that emits a single photon every time I excite the quantum dot, and I can collect all these photons with very high efficiency. But it's actually also much more. This beta factor actually tells you how close am I to have created a 1D world, if you wish, because if beta is 1, then the photons can only be emitted into the waveguide. It doesn't see anything else. It's like a 1D world that this quantum dot is living in. And in 1D, you have many other properties like emitter interactions and so on. I'll return to that a little bit later. It's also a figure of merit for really advanced applications of quantum optics, because it's linked to what we call the quantum cooperativity, that is beta divided by 1 minus beta. That's a figure of merit of also how we can use this platform to build photonic quantum gates. It's also for building multi-photon entanglement sources, and really a bulk of a number of advanced applications of that. So it's not just a source of single photons, it's really also the efficiency with which I can interface a single emitter, so the quantum dot, and a single photon. How it's a light matter interface, and how efficiently I can interface those two with each other. And if this cooperativity is really high, I would have a deterministic photon emitter interface. Every time I send in a photon on the emitter, it has to interact with the emitter. And there are a lot of details in that, and I'll not dwell on all this here today. But this simple relation I'm writing here, that the cooperativity is just expressed in terms of beta like that actually only holds if I can reduce all decoherence processes in the system. And this is really what is quite exciting on the platform today, that you can reduce decoherence. Decoherence is a big deal, of course, in any quantum system. There's disturbances that will decohere the quantum states I have. It's charge noise, it's phonons, it's nuclear spin noise, and being able to reduce that in your system is really key for all the advanced quantum applications. And if some of you are interested in more about this deterministic photon emitter interface, recently put on archive this manuscript, which is kind of our perspective blueprint for the technology, what you can do with these deterministic photon emitter interfaces in quantum technology. So back to chiral coupling, which is a key thing that we are interested in here today. And let's now just look at a very specific case on this platform. So now I take the most simple planar nanophotonic structure that we have in the lab. That's just what we call a nanobeam waveguide. So as again, 160 nanometers thin membrane and a waveguide consists of a few hundred nanometer width. And that's just a suspended structure that you see here. And what you have at the end here would be gratings, so that you can launch light into the waveguide, and you can also couple light out of the waveguides again. So here we just calculate, so how good is it then in terms of this directionality and also for the beta factor? And you see here a cross section of the geometry of this nanobeam waveguide in the YX plane here. You see it's a rectangular cross section. And if I calculate the directionality for a circularly polarized emitter, I would put inside the nanobeam waveguide as a function of the X coordinate here. You'll see I can actually get perfect directionality at a certain distance here, somewhere around here. You will have, really perfect directionality. And it changes sign when going from minus X to plus X as it should. So that would mean a sigma plus polarized emitter would emit only along one direction, not at all along the other direction. But it could also leak out of the structure. And that's what is captured in this beta factor that I introduced before. I can calculate also what is a beta factor, what's the probability that I get a photon in the direction that I would like to, as opposed to in the other direction or leaking out of the structure. And in these nanobeam waveguides, you can get beta factors of up to 70%, directional beta factors, I get it in the direction I want to. There's some leakage out of the structure because you need more advanced nanostructures, photonic crystal waveguide nanostructures to get the beta factors even higher. But this is quite sizable even for simple structure like that. 70% of the emission of the single photon emitted by the quantum dot would be collected by the structure and go in the direction that I would like it to. So we have worked a lot on this engineering the platform, as I briefly mentioned in the introduction, because that's really what we very well can do in photonics. As I said, we can really make these photonic nanostructures as we want with e-beam lithography. We can start to move holes around within the unit cell of the photonic structure. And in particular, we have figured out that if you are breaking the mirror symmetry, so again, here's a photonic crystal waveguide, here's a photonic crystal lattice, here's a photonic crystal waveguide. In a regular photonic crystal waveguide, you have symmetry along this, you have mirror symmetry along this direction, or this axis here. And as a consequence of that, you'll see that the block modes that are propagating along the waveguide here, that's what is plotted, projections of this block mode over here, it's actually preferentially linearly polarized. So here you see the projection onto the EX component of the electric field, the EY component of the electric field, and you see that it's either EY or EX. You see there's little overlap between EX and EY, and this exactly means that you have preferentially a linear polarization in a photonic crystal waveguide. And that's a consequence of this mirror symmetry here. And there's nothing that prevents us from breaking this mirror symmetry. So we have introduced what we call glide plane waveguides, where we make a glide plane symmetric translation of the, say, the upper part here. We are translating that by half a lattice constant, breaking the mirror symmetry. And now you see, if you calculate the block modes along this waveguide here, now they are projected down onto right-hand circular polarized components and left-hand circular polarized component, and you see there's little intensity overlap between those two. That means that actually spatially, preferentially, you have introduced circular, in-plane circular polarization in these structures. It's not that it will all be circular polarized. Everything, that's important to be aware of, everything will be spatially dependent. There will be points here with perfect circular polarization, and then you change when you're moving around in the unit cell here, you're changing the ellipticity of the mode, so you get a change from circular polarization to elliptical polarization, and there will also be few points with linear polarization. But this structure has been engineered to preferentially have circular polarization. So that's a whole idea of these glide plane waveguide structures that we have introduced. Here you see the band structure of the dispersion relation of such a waveguide mode. So this is a frequency as a function of the wave vector, the projection along the propagation direction, so along the Z direction here. You have a band gap region that is in between the black areas here, and this is where the waveguide modes are. So here you see the waveguide modes that are these modes that live here in the band gap. This is called a light line. So above the light line, so that would be the green shaded area, that is where the block wave vector is small. So the Z component along the propagation direction is small. That means that the X component, or the out of plane component, is large, and those will be leaky modes actually. So that's the reason that the beta factor is not 100% in our system, because there will always be, that light can be emitted totally vertically out of the structure. But the name of the game of these membrane structures is to suppress this leakage as much as possible, so you can get beta factors becoming very, very small or very large, sorry, by having a very little overlap with the modes that are leaking out of structure. And how good that is, we can see on the next slide here, because now we have we look in detail at these glide plane waveguides and see how good they work. Now there's a question, so let me see. What if the holes? So that's from Bahit Saskari Adakani. What if the holes distributed randomly around the waveguide? What if the holes are distributed randomly around the waveguide? You can unmute yourself and if I don't answer your question properly, but let me just try. I think maybe that's a question about what if there's disorder in the structures. So you have just these calculations are for perfect structures where I've introduced these glide plane symmetric waveguides and calculate what is the structure. What if I have disorder, which I would have in any system? And this is a very, very good point. I think in the fabrication we can make the position of these holes very, very precisely. So this is determined by E-beam lithography. The main disorder in the system is actually roughness on the holes. So when we're etching the holes here, there will be a little bit of roughness that scatters light, and that perturbs the system. Obviously, it's a perturbation to the system. So it doesn't mean that this band structure or the performance that I'm describing here changes. What it means is that if you'll get a new length scale in the system, and this length scale is how far does the light propagate in the waveguide on average before it scatters, and the main scattering mechanism, the worst scattering, or there are several, but actually the worst is the backscattering, that the light will be scattered back in the waveguide along the other direction. And then it can also be that it scatters out of the structure, so it leaks out of the structure. That's another scattering mechanisms, and those are statistical parameters. So what you can do is you can measure how long is this length. It's called a localization length, or the scattering mean free path. What you want to do for all this quantum optics I'm talking about here is you want to make devices that are shorter than that, so that the probability to scatter back is really small. And can you do that? That's a very non-trivial question. The answer is yes, you can. And that really has to do with how large a photonic crystal structure do I need to build before all these high beat effects and stuff I'm talking about here actually works and builds up. Is it fine with 5 or 10 or 100 holes, rows of holes? How many do I actually need? How large a photonic crystal does it take before a sizable optical local density of states is built up? And it turns out in these structures, because the refractive index contrast is really, really high, you need very little actually. So even very small photonic crystals, 5 micron long photonic crystals, for instance, would be perfect to have these very high beat effects. And the mean free path, if you make the fabrication well and avoid introducing too much disorder, typical numbers can be 20 microns, 50 microns, something like that. So therefore, there's room there to make short devices and thereby not be limited by this fabrication imperfection. But it's a very important point. There's another question: what are the strategies to avoid leakage? So the main leakage is leakage out of structure in the third dimension. Maybe I'll actually answer it with the slide I came to, because I introduced the nanobeam waveguides and said that the beta factor, we calculated the beta factor could be about 70%. So that would indeed mean that there is a 30% leakage out in the vertical direction, either going up or going down. In the photonic crystal waveguides, it turns out that this leakage can be really, really highly suppressed. That is because it's several effects actually. It's this membrane structure that we create, this 160 nanometer thin membrane, actually means that the cone of K vectors you can couple to, because of total internal reflection at the interface, it's a very small cone. So there's not so much leakage. There's not so many K vectors to actually leak to. Then there's another trick you can play in photonic crystals. That is, you can actually enhance the coupling to the waveguide mode. And that's exactly what you do in these photonic crystal waveguide structures. So here you see the glide plane waveguides. So you see we have broken the mirror of symmetry, and we are asking, so this is just theory, we are calculating how efficiently does a circular polarized sigma plus polarized emitter to the right in this direction as opposed to going to the left, and as opposed to going leaking to any other mode. So that's what the beta factor tells you. So that's a leakage, or that's a coupling to your preferred direction as opposed to leaking to any other mode. And here you see a calculation of this directional beta factor. This is within the unit cell of the glide plane photonic crystal waveguide. So it's a spatial map of that. And you see, so everything, as I pointed out, varies spatially, but the glide plane waveguide structures are engineered in order to have a preference for this circular polarization over large spatial areas. And that's why you are seeing that the beta factor here is high. I mean, the numbers are, there will be many areas here where you are in the high 90s of this directional beta factor. And the highest points here would be 98%. So that really means that only in 2% of the cases you will lose a photon to coupling vertically out of structure. Why does it work so well? Well, because of this membrane leakage that I mentioned just before. But another point as well is that we can do Purcell enhancement. We can exploit Purcell enhancement, which is enhanced coupling into the waveguide mode, meaning that I'm suppressing this coupling to radiation modes, but I'm also enhancing the coupling to the mode that I'm interested in, to the left going mode, for instance, or to the right going mode, whatever directional mode I'm interested in. I'm enhancing this as well as suppressing that. And that's a way to get beta to go very high. How do I enhance this? Well, that's called the Purcell effect. And many of you have heard about the Purcell effect in cavities. If I put a quantum emitter into a cavity, then it decays faster. And there's a Purcell factor that is proportional to Q over V. So if I have a high Q factor on a small mode volume cavity, then this Purcell speed up goes faster and faster. The quantum emitter likes to emit a photon into a mode that is small and has a high Q factor. The local density of states is enhanced for this mode, and that enhances the spontaneous emission. Spontaneous emission is not just the property of the emitter, it's also the property of the environment. In a waveguide, we have a similar effect, but in this case, it's not a Q factor because there's no mode being resonated here. There's a propagating mode you are coupling to, and this propagating mode has properties and one important property is the group velocity of that mode. And it turns out, so the group velocity is d omega decay. So if I'm going back to my dispersion relations here, these are the waveguide modes we're interested in. This is omega as a function of k, and you see that we have engineered the dispersion of this light. Omega doesn't depend linearly on k in these photonic crystals like it would in free space. You have a non-linear dependence of omega on k. That means the omega decay is actually, so the group velocity is lower than you would have in free space. So you're slowing down light in these photonic crystal waveguides. If you're slowing down the light, you're enhancing the density of states, and you get a Purcell enhancement from slow light. So you can say the quantum dot likes to emit its photon into a slowly propagating mode because its density of state is higher. So that's a Purcell enhancement in a photonic crystal waveguide, or in a waveguide geometry, which is generalization of the Purcell enhancement you will have in cavities. So that's a trick we are playing to. That was a long answer to a very good question. So to avoid leakage, we're enhancing the coupling into the waveguide mode by this slow light enhanced induced Purcell enhancement. We are suppressing the leakage to all the other modes. That's what the photonic band gap does, and that's what these membrane structures do in the third dimension. And it's really this combo that means that these numbers can be really close to unity. They will never be 100%, but you can get really, really close to unity. You can get 99% plus. And the limiting factors for all the quantum applications here would not be beta factor. Beta is perfectly fine. It's more about decoherence processes, actually. Okay, so how am I doing on time?
You are running out of time now.
Yes. So is it time to take a break now?
Yeah, you could take a break now, or
let me just let me finish off with this one, then we take a break. Then there's a natural break. So this is just an experiment we conducted quite some time ago now on these glide plane waveguides. Of course, also showing that it works in the experiment. So here you see a scanning electron microscope image of the structures that we are making. This is a composite structure that has glide plane symmetry at the bulk, or in the center part of the device. So if you look at zooming in, you'll see that this mirror symmetry is broken here close to the center. And then when you go further and further out to the side of the device, we are gradually changing the whole. So we're going back to regular photonic crystal symmetry, because these block modes we can better couple out to regular waveguides and out to these grading couplers that I talked about. So this is really showing some of the engineering again you can do in these structures, that you can design the waveguide and the properties of the waveguide the way that you would like. So how do we show the directionality? In this case, we are identifying single quantum dot lines A and B here in particular, and we are then simply looking here to the left and to the right on those two gradings here, whether a quantum dot emits to the left or to the right. And you see here in this case, where we are not applying any magnetic field to the system, we are collecting from quantum dot A line, we are collecting photons both on the red grading and on the blue grading. So it's emitting half the time one direction, half the time the other direction. In this case, it's a linear dipole transition. So there's nothing. You have to have a circular polarized transition to get this directionality. And this is exactly what we see when we are starting to apply a magnetic field in the growth direction of the quantum dot. You split the lines. One of the lines would be a sigma minus transition. Another one would be a sigma plus transition. And you see, for instance, here the sigma plus emits almost exclusively to the red grading here, and the blue, that's a little bit of grass here. So it hardly collect any photons on the blue grading, and vice versa for the sigma minus transition. And then just as an experimental check, you're flipping the polarity. You're instead of having the magnetic field in the plus direction, you put it in the minus direction. That flips the polarity so that minus becomes plus, sigma minus becomes sigma plus. And indeed, we then also see that this also, I mean, the sigma plus wants to emit on the red grading and not on the blue. You can, of course, then extract this directionality and quantify it. This is what is done here, and also prove that this is really single photon emission. So these are single quantum dot lines emitting single photons. You do this in optics, what is called a Hamburg-Brown twist experiment. You take the light on the beam splitter, 50-50 beam splitter, you send it out to two detectors, and you do coincidence detection between those two detectors to see how often do I detect a photon in each detector at the same time. If it never happens, then that was a single photon source. This was a single photon pulse that we have generated. And of course, nothing is perfect in real experiments. So here you see a little bit of multi-photon contribution in these experiments. Good. So I think we'll take a break here.
You will need to share your screen again, Peter, once you start. And there is a question by Ramesh, both in the chat. You in the Q&A, you can find it.
Yes, I see it. Thanks. I'll need to share my screen again. Okay, I think we start again. So you can still hear me. So there's a question from Ramesh Tamanka. He's asking, why is the intensity at A and B different without the magnetic field? And referring to the experiment that we had here, this very good question. Indeed, if you look carefully at these plots here, you'll see that, well, the red and the blue curves here are not exactly the same height. And that really has to do with asymmetries in the experiment. So you'll see that there is some the photons are propagating out of the region and into the grading, and there will be some slightly different propagation lengths. And I think most importantly also is that there can be a little bit different coupling out of the grading and into the actual microscope objective that we are using for the measurement. So that will give some asymmetry in the data. So this is a very good point. So that's uncertainty in here, but then when we are applying the magnetic field, we are seeing a very pronounced change in this overall intensity while not changing any parameters. Thank you. So let's return here to slides. This slide, oops. Yes. So I'm missing something here, I think. There's something missing from the slide, but that's I think it's all right. So topology. So there's also topological photonics. There are opportunities of so far I spoke about glide plane waveguides. So though there's nothing that is topologically non-trivial in these systems, but there's an opportunity also to make structures, photonic crystal or photonic waveguide structures, where you are combining, interfacing two photonic crystal sections with that have different topological properties. So that would be this is an example from the literature from Edovax and Mohammed Hafezi, where they're taking two lattices, and there's a Chern number associated with each of these photonic lattices, and you're combining those two that have two different Chern numbers. And at the interface between those two lattices, you can start to have waveguide modes as well, just like in what I've spoken about before. I mean, we are deliberately leaving out a row of holes, and that was our waveguide mode. Here it is the edge mode featuring that shows up in between the regions of those two waveguides with different topological sections, photonic crystal sections with different topological properties. And this is really an interesting area where the same physics that I've been spoken about so far, I mean, this directional emission also shows up. And this first experiment proved that. This is an experiment just like what I showed before. You're applying a magnetic field and you're having sigma plus and sigma minus transitions, and you're collecting photons from different different gradings here, and you're seeing that sigma minus goes to one grading to the left and sigma plus goes to the other grading. And then they can also make bends in these structures as you see here. So if you're starting to if you're introducing a structure like that where you are extending this photonic crystal section, then I think I should shut this down. Oh yeah, that's better with my cursor. You're extending this photonic section here, you can actually have a waveguide bend, a 60-degree waveguide bend like that they also showed explicitly that it works. And I think there are really some interesting questions about what are the photon transport properties of these topological systems here, and could it be that there would be some advantages in terms of these backscattering links and processes that I was briefly mentioning before? Maybe these topological waveguides would be better. Now there's a question: which symmetries are broken in the photonic crystals? So but maybe I will show it on the next slide, so you can see more precisely what the waveguides look like. So this is what we are doing in this direction within TOCHA, the project that Sergio is leading and that he introduced in the beginning. Now we are starting to make these kind of topological interface structures, and you see here really a close up of the structures that we are making. So here you see really the unit cell, and here's one photonic crystal up here, and here's the other photonic crystal down here. And you see we have translated by half a lattice constant, so making this glide plane waveguide trick as well. And then we have mirrored also the unit cell. So that's the two operations that are being done on a unit cell. And you see these structures like you saw before. That would be such a, now it's a topological interface where the photons are guided in this region. It doesn't, you just looking at the image, you wouldn't think that photons would be transporting there. There's really not a waveguide like what we had previously, but there are two photonic crystals with that have different Chern numbers, and at the edge of those two structures you can get photon transport, just like in the waveguide structures that I introduced before. And you see we make again these advanced devices where you are okay. Then there's a question about what is the mode of this at this topological, at this interface here. How does this mode look like? So this can really be you can calculate them, and you see some images here. Let's not go into all the details about this, but it can be quite a complex mode because you're really starting to do quite advanced engineering of your unit cell, of your photonic lattices, if you wish. So can I couple this mode out, and can I couple it out to these gratings that I eventually want to get photons out from? And there's a lot of engineering going into that you are starting to adiabatically transform these modes, these defect modes, or these modes between the two photonic crystals, photonic sections, and you're gradually changing this mode into something that you can couple into a nanobeam waveguide and eventually couple out with a grating. So that's really mode engineering, adiabatic mode engineering, that works surprisingly well, actually, that you can do it with quite high efficiency. And this is all stuff we are working on at the moment, but it looks surprisingly efficient, actually. In this particular experiment, we have been after also this how much slow light can I then ultimately achieve in these structures. A way of measuring slow light is actually that you are using that you can have residual reflection at these interfaces, so that the reflection, you have a weak cavity formed actually between the two output gratings, and you can use that Fabry-Perot fringes to extract the group index, so the slowdown factor of the photons transported in these advanced photonic waveguides. And those are the numbers that we are achieving at the moment. I mean, slowdown factors between 6 and 8, which enhances the light matter coupling into the waveguide, as I mentioned before, by the Purcell enhancement. Okay, so that was a lot about photon emission, directional photon emission in engineered photonic crystal-based waveguides. So now we want to go one step further and say, well, can I use that to do something else than just directional emission? That's cute, but maybe what else can I do? Can I get photon transport to become directional, so that I can, make non-reciprocal photonic devices where I send light in through one direction, and that does something else, and if I send it in from the other direction? Can I break time reversal symmetry from the point of view of light? Well, the waveguide clearly doesn't do it, right? I mean, there is reciprocity in Maxwell's equation. So you have nothing like, if I send light on one direction in the waveguide, light cannot go through the other direction of the waveguide. There is light, and it just, you get a complex conjugation there that we spoke about in the beginning. The key is really the light matter interaction, because the light matter interaction is directional. D.E again, that we spoke about at length. That is not just about how does the emitter emit light. It's also about how does the emitter scatter light. So if I send in photons in the waveguide and have interaction with the emitter, that would be D.E that determines this interaction, and that will be directional. So there should be a difference if I'm going from left or going from right, if I engineer D.E to be directional, and we now know how to do that. I'll be speaking about quantum emitters because that's what is close to my heart. But of course, it doesn't have to be quantum. So I just have a single quantum dot and with a single electron, a single spin in there. But I could also have a classical polarizability, so that you could get this interaction to become directional. So it's a more general concept here than just for the quantum light matter interaction that I'll be speaking about. Okay, so I already introduced it. So now the idea is that I have the emitter, and I have it in the sigma plus polarized a transition dipole. I send light in from the right, and D.E is set up so that this emitter can only emit to the right. That also means that that when I do scattering on such a quantum emitter here, it cannot scatter the photons off to the left. It can only scatter in the forward direction, at least if the directional beta factor is perfect. Of course, in reality, it will be finite, and there will be a little bit of probability of scattering backwards, but prominent, dominating probability of scattering forward. The transmission coefficient here it is. If I take a narrow band single photon pulse, so containing just a single photon, but it also holds if I take a narrow band classical field, laser field, but just attenuate it so much that on average only at max one photon interacts with the emitter at a time. Narrow band, what does that mean? Well, narrow band relative to the bandwidth of the emitter. So the emitter will have a bandwidth of gigahertz, something, a quantum dot. So I'll need to take a pulse that is narrower than the line width of the quantum dot. Then the transmission would be 1 divided by 1 minus 2 times beta directional. Beta directional could be close to unity, as we talked about already, could be 98% at least. So you see, if you put 1 into this equation, you'll get a -1 from that. And what does that mean? That means I get a transmission coefficient in the that it scatters in the forward direction with a minus in front. So that means that the photon has acquired a pi phase shift in the interaction. So that's what happens. I send the photon in, beta directional is very, very high. So the photon scatters, can only go forward, but in the scattering process, it acquires a pi phase shift. Okay, now I send the photon back again. D.E was optimum for going forward. It comes from the wrong direction. D.E would be 0 going in the backward direction. So it doesn't see the emitter at all. D.E is 0, no phase shift, no interaction with the emitter. So here you see the difference between going forward and the difference between going backward, a pi phase shift. Okay, so now I can make a non-reciprocal photonic device based on this, because how do I turn a phase shift into a different direction? Well, that's called a Mach center interferometer. I take 2 beam splitters, and this is then I stick in this glide plane waveguide with a high directional beta factor and this directional light matter coupling. I send in a photon. This is a 50-50 beam splitter, so 50% probability it goes either direction. If it comes here, it acquires a pi phase shift, and then the 2 arms combine again on the second beam splitter here. But now, due to the phase shift here, this Mach center interferometer will be unbalanced. So the photon will end up in the same port. So say the down port as it entered if it entered in the down port. It's asymmetric now. There's a pi phase shift in one arm. If I send the photon back, well, it doesn't see the emitter anymore because D.E is 0 for going backward. Now it's a symmetric Mach center interferometer, so a photon coming in the down port will exit in the up port. So you see, I made a non-reciprocal device. I send in the photon in this port, and when I send it back again after 2 interactions with the emitter, well, in one case it did interact, and in the other case it didn't interact at all because the coupling was 0. The photon ends up in another port that it enters. So that's a non-reciprocal photon device, a single photon device. It's controlled by just a single emitter. So it's just a single quantum dot sitting there deciding what happens. And of course, we know quantum systems, we may operate in quantum superpositions. So I could have prepared a spin state, for instance, where I both had a pi phase shift and not had a pi phase shift at the same time. And then you can end up with these awkward situations that you both reflect and both get a phase shift and not get a phase shift. And this is actually, and since as I said, also it works even for classical fields. It doesn't have to be a single photon I send in. It can also be just a weak classical field. Then this is actually a way of making a Schrödinger cat state where I both send the classical state to this arm or that arm simultaneously, and it's controlled by just a single spin. Okay, so you can also make quantum gates based on that. I think I will skip the details about this here, but these are actually quite handy tools. That's maybe the take-home message here. That you can make a quantum gate, a C0 gate for photons, where one photon being in a superposition between 2 waveguides here, a control photon actually controls the target photon that is sent in subsequently, and I effectively mediate a photon-photon operation, C0 operation, by the directional coupling to the spin or in the quantum dot here. And that is a way of doing some of the things that is really hard to do for photons. Non-linearly interact with each other. It's a 2-qubit gate between two photons mediated by this coupling through the quantum dots, which is the challenge also for quantum computing and advanced application of photons, that photons are good at really many things, but mechanical 2-qubit interactions, that is just really hard. The photon emitter interface here gives you a tool, a way to do that. And the directionality, the chiral coupling, comes in as a quite handy tool here, actually as a quite practical tool to get the photons in and interact with very high efficiency. So here I brought an example from about this non-directional photon transport now, non-reciprocal photon transport. This is a beautiful experiment on atoms done in Arno Rauschenbeutel's group, then in Vienna, now in Berlin. So they are trapping atoms in the vicinity of these tapered optical nanofibers that I also mentioned in the beginning. They also have what's called a whispering gallery mode resonator. So that's a resonator where you are sending the light through many rounds through such a ring cavity essentially. And again, you'll have the atoms sitting here just very close to the surface of the fibers and of the resonators, and you'll be trapping the atoms there. And right there in the evanescent tail of the field, you'll have a quite sizable value of the longitudinal component of electric field, and you can have close to circularly polarized electric fields there, and that means directional emission, as we have learned. You can say in the atomic systems, the beta factor will not be so extremely high, because you can imagine that if I have an atom trapped here, then that could radiate quite a lot out to free space and not just into the resonator, into the nanofiber. So these very high beta factors that we are talking about in the solid state systems with the quantum dots, you won't have in atomic systems. On the other hand, for them, it would be much easier to take multiple emitters. So having many atom experiments is something that they can do and boost their coupling efficiencies in this manner. This is something that is much harder for us to do on the solid state platform. And that's just two different regimes also of the applications of these kind of systems. The physics is very much the same. Okay, so they did a great experiment here where they're sending light through these nanobeam fibers. And I think they did both for the resonators and the fibers. Let's just look at the fiber case for simplicity. They sent light in from left to right, and in this case you have the circular polarization, and we polarized emitters here. In this case, d dot e is small, so you don't have much interaction with these atoms that are sitting there next to the fiber. If you send light in from the other direction, from right to left, you have the right circular polarization to interact with the emitter. You're exciting the atoms, and the atoms actually in most cases just radiate the photons out of the structure. So you lose the light in that case. So this is actually an optical isolator. You can get light through one direction, but if you try to send it in through the other direction, it's radiated out by the atoms to free space. So you're attenuating the field. And it only works by this because of this chiral light matter interaction. That means that, again, this d dot e thing that we're playing with all the time. Here they have measured then the isolation of this going in the two different directions versus the chirality, where they're changing the polarization of the mode that they're sending in from the nanobeam waveguide. And they see that this directional coupling means that you can attenuate the beam simply by radiating out to other modes. Okay. Yeah, so these are other examples from Arno's group, Rauschenbeutel's group, and also from Barak Young's group, atomic physics groups that take it one step further and use this really to do optical routing. So then they can send in again light through one waveguide here. Now you're coupled to this resonator here, and in one direction it does not interact with the atoms that are or maybe there's one atom here that is trapped then in the vicinity of the ring, like here, for instance. In the other case, you do interact with the atom because d.e is optimized for it, and you will get different phase shifts in this resonator. So that means that you can, in one case, you will, pass right through. You'll go from 1 to 2. In the other case, if you send it in through the other direction, you'll get a different phase shift from the interaction. So you'll mean that you'll go from 2 to 3. So this is really routing with a single atom of the light sent in through different directions through the waveguide. So a little bit more details about some of the new opportunities here, also for new physics, and also quite open questions here, because it's really a new paradigm, you can say, in light matter interaction to have this directional emission. And so far I spoke just about a single emitter, and could give directional emission. It can also get directional scattering, and these directional phase shifts that were used for non-reciprocal photonic devices. And you can ask about what happens if I start to take multiple emitters in these waveguide systems and start to directionally couple them to each other. And I would say already two without this chirality is quite interesting physics, because as I said also in the beginning, I think when the beta factor is so high, then it's like if the world was 1D. So how do two emitters interact with each other? That dipole-dipole interaction, and that decays quickly as you move these dipoles away from each other. The interaction decays as one of our cubed, this dipole-dipole interaction. But in 1D, it's not like that. You'll actually have infinitely ranging dipole-dipole coupling. So when I have a beta factor that is so high, the quantum emitter believes that it's in a 1D world. It can only interact with a single mode, and that means that putting those two emitters even far away from each other, they would still interact through dipole-dipole interaction. Okay, so now we are adding this directionality to this game. So now I'll have two emitters. They are circularly polarized emitter sigma plus, and they can only directionally couple to each other. So the one to the right here can see the one to the left, but the one to the left doesn't know that the one to the right exists because of that's directional coupling. And that of course changes the physics. So what happens with dipole-dipole interaction is it gets super radiant state and sub-radiant state. That is really due to also that you have symmetric coupling between both directions, that you start to create these super and sub-radiant eigenstates of two entangled, two coupled emitters with each other. When I have directional coupling, that changes. So you'll start to couple those two, or you will start to interact and entangle those two quantum emitters differently, where this chirality becomes an additional complexity. And more generally, I think there's really a bulk of new opportunities that can be explored here, because those are just these sub and super radiant states are just the matter states and how they can be coupled to each other. And that's only just a few excitations in the system. If I have one excitation shared by those two emitters, but now if I start to send photons in to these emitters, then I have the nonlinear interaction between those photons coming into the emitters and doing really a highly nonlinear quantum interaction, and it's really a very interesting and open research questions on what quantum states and what many-body coupled states of light matter can I engineer, can I possibly make, where you're having that very efficient and chiral or directional coupling between emitters. And it's a really complex system where you because it's a big Hilbert space, you send in photons, and if you start to launch more photons and have them nonlinear interacting with the emitters here, it's a quantum system that very quickly explodes. And I think some analogies with electronic systems and electronic transport systems are really interesting to think about, where I think this directionality is something that directional coupling between emitters is something quite new and possible to engineer here in your on your photonics platform. So there are many people really looking into that and seeing also complex behavior like photon bound states, how they're forming due to the interactions and the role of the chirality for that. And that's a really hot research topic. Peter Soller, Derek Chang, many others are looking into. I will give you just an example of what we are particularly interested in and working on in this direction, because chirality and chiral coupling here gives you an interesting opportunity to in the realm of spin physics. So I didn't speak about spins before, but you know, I can also tunnel in a single spin inside the quantum dot, and now I'll have a 4-level system like indicated here, where the spin state could be, I prepared the quantum dot with spin state down or with spin state up, and then I can excite this system to what is called charged excitons and have those two different possibilities of that. So those transitions here, this is a sigma minus transition, sigma plus transition, circularly polarized transitions. So I can play all these tricks with directional emission. And then you see what I can do, what I can apply as a very practical thing, apply the directional coupling for would actually be as a, to read out the optical spin. If I have some kind of spin state, I'm not really aware of which one it is, I will excite the system and emit a photon. If it emits a photon to the left, it was a sigma minus spin, sigma minus transition. The spin is pointing down. If I get a photon click in the detector out here, a photon in a click in the detector over here, it will be in the spin state up. So it's really a way of reading out the spin state by just seeing at what direction did the photon go. I can also actually use it to produce path entangled states, because spins, of course, we can prepare in superposition state of down and up at the same time. And if I then excite this system and it emits a photon, then, well, it can emit on each of those transitions. And if it emits on the sigma minus transition, it goes to the left. If it emits on the up transition, it goes to the right. I do not know which one happened. So I'll end up in a in an entangled state. If the spin was down, it emitted a photon to the left. If the spin was up, it emitted a photon to the right. So that's a way of making spin photon entanglement. And then there's a very nice and interesting generalization of that, that you can use that actually to produce multi-photon entangled states. Because I can repeat this many times. I can excite the system and emit, it produces spin photon entangled state. I can do a rotation on the spin, and then I can do it again, excite, emit, excite, emit, excite, emit. This is what we're very good at on the quantum dot platform, because of these beta factors are so high that I can collect the photons with very high efficiency. And it turns out if I do it n times, then I'll get an n photon entangled state. It's called a GHZ state, Greenberger-Horn-Seilinger state. That's really a multi-photon entangled state, that if the spin was pointing down, then the first photon was emitted to the left, and so was the second, and so was the third, and so on. But if the spin was pointing up, then the first photon was emitted to the right, and that holds for all subsequently emitted photons as well. Yeah, 5 minutes, thank you. So yeah, that's just a very practical application of this photon emitter interface and the chiral coupling there to start introducing and making entangled states, multi-photon entangled states. Okay, I think I will. Let's see. Sorry. I think I will end with this one as another little application of the directional coupling, and that is emphasizing also the nonlinear properties of this. I already said something about it, that I had one photon. I just very briefly said one photon interacting with an emitter. That that this interaction means that if I send in another photon at a different time, then I effectively mediate a nonlinear quantum gate between those two photons. And I can do something else. I can actually send two photons or superposition of 1 and 2 photons in on the quantum emitter at the same time. And because the beta factor is so high, and I have a quantized emitter, 2-level system in the most simple case here, then it can only interact with 1 photon at a time. I cannot interact with, I cannot excite an atom quantum dot with 2 excitations. It can only 1 at a time. It's a quantized emitter. There's a Pauli exclusion principle that prevents me from doing that. So that means if the beta is so high, then there should be a difference. If I come in with a superposition of 1 and 2 photons, it will have to do something differently to them. It will scatter. We talked about that already. We in this chiral coupling, if I send in a photon, I'll get a pi phase shift on the 1 photon component, and that's not much else is happening to that. But the 2 photons, they will have to be distorted by the coupling with the emitter. I'll come in with a 2 photon pulse, and there's some probability that the photon comes first in this pulse or late on the pulse, and that will distort this pulse because it will create quantum correlations and quantum entanglement by the interaction with the emitter. So 1 and 2 photons will be scattered into different spectral temporal modes, simply because of the Pauli exclusion principle prevents the quantum emitter from interacting with more photons at the same time. And what we worked out here is actually a way of making use of that distortion. It's a highly complex thing. I send in a pulse of light. That's a multi-mode system, and I start to change that pulse of light due to the interaction with the emitter. It's surprisingly rich and complex, even that system. And here we worked out a way that you can actually make use of that distortion. So if I control the pulse lengths here properly, I can actually end up in a situation where these 1 and 2 photon components are scattered into different spectral temporal modes that I could possibly separate from each other. So that's what's called a photon sorter. I could have a device that I send a superposition of 1 and 2 photons into, and out in one mode goes 1 photon, and out in another mode goes 2 photons. And it turns out that to get this to work, you actually also need something that selects a specific spectral temporal mode, and we can do nonlinear conversion to actually do that. I think I'll skip the details here. But the bottom line is the following: that now I'll have a photon sorter, a scatterer that I send in a superposition of 1 and 2. I do spectral temporal mode selection, and then I will have 1 photon component going out in one direction, 2 photon component going out in another direction. The modes are being, or the 1 and 2 photon components are being split into 2 different spatial modes. And that is one of the things that is hard to do in photonics, because it's a nonlinear interaction, right? I have superposition in, I get 1 out in one arm and 2 out in another arm. So that's exactly what photons have troubles with, and that means that many of the quantum computing or quantum application of photons are trying to circumvent these kind of challenges, that they don't have good nonlinear interaction. And that's actually the reason why many quantum computing architectures and so, I mean, the resources are dramatic when scaling it up to advanced applications. You need ancillary photons in order to do that. So now the interaction with the emitter here, the light matter interaction with the emitter, is actually a way of doing it. And here you have worked out, that's a technical thing, but a way of exploiting particularly this photon sorter actually do what's called a Bell measurement, that you can, if I send in any combinations of path encoded Bell states in these 4 waveguide modes here, I can, with photon detection events here, I can actually say, or I can with certainty say, depending on where the photons end up, what Bell state did I actually send into the system. So that's called a Bell analyzer, a deterministic Bell analyzer, and it also even enables you to make quantum gates. But let's skip this. I think I will wrap it up here. I think we have covered most of what I wanted to say. Some of these things with the photon non-linearity, that's what these slides about, also work in the lab. So we see single photon non-linear operation very well in these systems. Decoherence that I said absolutely nothing about today is key to get these things to work, and also the multi-photon entanglement sources that I briefly mentioned. Any decoherence processes needs to really be dealt with seriously, and that is that is another talk of really explaining about I think the good news from the platform that decoherence properties are starting to come along, so that we can start to do really advanced applications of this hardware. And then I will end with this little announcement of the summer school that Sergio was also mentioning. So the summer school, it's called Topological Bosonics and Electronics. So the idea is exactly what Sergio was alluding to, bringing together communities in photonics, phononics, and electronics to start first attempt to start getting a common language, and maybe exploiting some of the concepts and also some opportunities for interfacing systems that would be really interesting to do. So this is within TOCHA, and you see the lineup of excellent speakers here, and I encourage you to sign up for this school. It will be a 3-day school, all on Zoom, from the 30th of August to 1st of September. So thank you very much, and I'm happy to take more questions.
Thank you, Peter. It was a wonderful tutorial. And now we have several minutes for questions. Please go ahead, type in the questions, or directly raise your hand. And then if there are more questions, you will have the opportunity to have a coffee with Peter in the coffee break. Please, I'll let you.
I don't see any questions immediately. Please, you're also welcome to unmute your microphone if that is easier.
Oh, first you need to raise your hand, and then we will unmute your microphone.
Okay.
I'll let you speak. There is Thanasis that has a question. You can talk directly, Thanasis.
Yes. Thank you very much for this very nice talk. Personally, I'm not in the field, so I have a very naive question. What about the temporal relation between the different photons? Whether the photons are interacting synchronously or after a time delay between each other and so on. Probably you mentioned that, but I may have missed the point.
Yes.
Is there any correlation at all?
Oh yeah, this is a beautiful question, and a very deep one actually. So so it really depends on it's something we can control in the experiments. And there are two regimes essentially. So there's regime where we start with just an empty quantum dot. So then it's just a 2-level system, and then there is a time memory, you can say, of your quantum dot, which is the lifetime of the quantum dot. So that's about a nanosecond or so. So that would be the time that the quantum dot can introduce interaction between two photons. So everything that goes on sub 1 nanosecond timescale will give rise to very complicated correlations actually between the two photons. If they're further away than 1 nanosecond, then it will just independent. It will be like two independent photons interacting with each other. If they're within the 1 nanosecond time scale, then you get and those can be 2 pulses. It could be 200 picosecond pulses that you're controlling the time in between, and then you can really start to play with these advanced correlations, and that's a surprisingly complicated system. It could also be a pulse containing 2 photons, but then it was like a 500 picosecond pulse or something that you're changing this pulse with, and those are 2 different experiments where you're probing some of the same physics of really, 2 pulses of light interacting with something with a bandwidth of a nanosecond. So there's another opportunity that I also briefly said, that is if you have a spin. If you have a spin, then you have a longer memory time in the system. That would be a microsecond time scale, and then you can start to also have more advanced, you can say, photon interaction also on longer time scales, and exploiting this spin degree of freedom. I don't know if that's answered your question.
Yeah, I understand that it's a very complex situation.
Yes, but you can think of maybe in the simplest case, if you say a 2 photon pulse, that would have a certain duration. So say it's 100 picosecond. So that means that there would be a probability that the photon comes in the tail of the pulse, or it comes early in the pulse, and that's all described by this wave function that you're sending into the emitter, and that is this photon pulse interacting with the 2-level system. That is what you're describing, and it matters if you have 2 photons in this pulse, or 3 photons, or 4 photons, or 1 photon, because you can think of the photons as not, they're not localized in time. It's not here it comes, right? It has a probability, amplitude, a wave function, and that is what goes into your when you're calculating that. That's a kind of the physical picture. 2 photon pulse will be distributed in time, and you should have this, and that's an interaction with a 2-level system that has a bandwidth also, because that's the uncertainty on the transition. That's this 1 nanosecond I was talking about. That's gigahertz bandwidth and frequency, and it's those 2 quantum systems you're interacting with each other.
Can we also talk about amplification in this interaction between photons?
Oh, yes. This is a wonderful question. And a very non-trivial one. Stimulated emission. so I mean, we all see textbooks of stimulated emission. There's a photon going in, and there's an excited emitter, and how does that stimulate? And then a copy comes out of 2 photons. It's much more complicated in reality, and that's exactly the physics you can describe here, because now we have interaction at the few photon level, so you can actually see, and you get a little overselling it maybe, but you're rewriting the textbooks here and really understanding how does this picture really look like of 1 photon stimulating 1 emitter. that is not the textbook drawing. It's something much more advanced and with degrees of freedom.
Asking this question, I didn't have in mind so much.
Sorry, you are falling out.
Stimulated emission, but the fact that in order to, sorry,
you're falling out. I cannot hear you.
Yeah.
Oh, now it's better. I think now it works.
Okay. Okay. When I asked this question, I didn't have in mind so much the stimulated emission, but rather I had in mind whether you can cascade basically the let's say the photon propagation over several devices, to say so, because I expect to have also some losses. And
yes.
And so how you can compensate about these losses? I was wondering whether you have some amplification so that you don't need to worry too much about cascading the operation over several devices.
Yes.
So.
No, well, it very much depends on what you're after. So you can say in we are doing quantum information processing, so we want qubits, and qubits we cannot amplify, so there's a no cloning theorem. And so I think if there are other things, yeah, I think it depends on what you want to do. So in general, these things that I'm talking about works pretty well for single emitters and few emitters, because it's really this local light matter interaction that you're exploiting. If you want to take a much more bulky device, for instance, and make an amplifier out of that and make that directional, it's I would not say it's impossible, but it's a much more tougher challenge of getting this directional coupling over a very extended spatial area. It works so extremely well in my case because it's just, you know, a few nanometer quantum dot. That's the interaction that we are engineering. If we want it over 100 microns, it's a different, it's a quite different game. It's not something we have been looking into at all. I would not say it's impossible, but one would have to certainly not jump to conclusions that you know that this could just be absolutely you know, a game changer or anything like that. My suspicion would be there will be no free lunches there, but
so Peter, you have
thank you very much for this inspiring talk.
Thank you.
So you have two questions, two raised hands.
Okay.
On the right.
So can please just speak the, I'm not sure I see them.
Clivia Sotomayor is the first.
Yeah, is that okay?
Yes.
Good. Okay, well, thank you very much for this very entertaining and very comprehensive lecture, Peter.
Thank you.
I have a question concerning, like, in the spirit of Docha. Well, I have two questions. Yes. One is the size of these structures, what technically is people call footprint, and how one can integrate it into something that will be looking like an application. I mean, you have some examples of integration, but it's very partial, and when it's a schematic, I think.
Yes, yes.
Yeah. So that's my first question. And my second question is, there are concepts which are intrinsic to topological matter and concepts that are intrinsic to quantum optics or quantum photonics. What would you say are the key concepts we need to have in mind concerning topological photons? That's the second question.
Yes, let me start with the first one. So, yeah, sorry, just so what was your
footprint integrity?
Footprint, yes, thank you. Yes, sorry. Yeah, so these devices are small. Typically the short waveguides would be I mean 10 microns or so. That is perfectly fine to get this very, very high light matter interaction strength, and it's also fine in relation to the disorder in the system. So this is one of the things that we are very interested in touch here also. Scattering mean free path. So maybe it's 20 microns or 30 microns, depending on how much slow light you have and so on. Maybe I can push these boundaries so I can get a longer scattering mean free path and still have slow light, and I can push the numbers there a little bit. And I think that's important to do because there's room already, because we can make short devices and we can get excellent single photon source, multi-photon entanglement sources, but giving us more more space, I think, is an important thing, and even a factor 5 or 10 or improvement could be quite substantial and important. I mean, it's also about, of course, improving your fabrication process even further. This is something that we are just starting on. I mean, and all is done in university labs and so on. So I think it's quite nice what can be done already there. And if you really push some put some engineering efforts into that, I'm sure you could be doing much better. So the footprint is really, you know, small devices, and there is already room to produce hardware for. I mean, this little non-reciprocal device that I showed would be something that is, you know, 10 micron long, and that you could interface. But because I think that's the other important point here, and it's a very good point. I'm not imagining that we would, you know, build on this platform, gallium arsenide platform, the whole photonic quantum computer or anything like that. I think you would like to interface like a hetero structure, or what do you call it? I mean, interface the active devices that we are having here to for instance, silicon nitride and ultimately silicon photonics. I mean, our wavelengths is not that silicon compatible with silicon photonics today, but this is something that will change in the future. I'm not worried about that. So we're thinking about an approach where we are making these source devices and we're interfacing it with advanced quantum photonic integrated circuits to do advanced quantum processes there. So really in a heterogeneous approach where you have sources, you're building more and more functionalities on the sources, and then you're coupling that to silicon nitride and silicon photonics for more advanced photonic processing. That is very much the opportunity that I see. And I went to this slide here because this paper that we put on arXiv is exactly on this vision about heterogeneous approach to quantum computing, ultimately, where we think we can produce deterministically with these small devices advanced photonic resources in a much more resource efficient manner than you can do with the parametric down conversion sources. So there's a famous company in the US, PsiQuantum, that is really, you know, pushing photonic based quantum computing and making lots of effort on the processing side. And I think our deterministic sources there could really be an add-on that would fit very well into their architectures, you can say. I don't know, did that answer your question, Clivia?
Yeah, to some degree, but I think basically the bottom line is that we are going to very heterogeneous systems, material-wise, technology-wise, in order to meet integration, compactness, and of course the performance of quantum computing type photonics application. Yeah. So my second question was on the concepts, or the topological matter, topological bosons, and the quantum photonics, quantum computing, the overlap. Where do you see the overlap?
Yes. Yeah, there I'm also I don't have very clear visions there, I would say. So for the directional emission, so this chiral light matter interaction, this is a neat tool that is very practical also for many of the devices. Topological photonics enables that, but you don't need topological devices in order to do that. I think that what I was saying there in the beginning, the backscattering, if you can use some of the notions or ideas from topological electronics and topological transport there to reduce backscattering in the devices, and therefore increasing the length. And you, Clivia and David, have been doing, Garcia have been doing interesting work really on this. If you can exploit that, I think that could be a nice thing and a practical thing. I'm also actually surprised how we're just starting, as you know, and also these kind of measurements, and actually it works better than what I had thought, because you have a quite advanced structure, quite advanced waveguide there, and this mode is quite complex, but we actually managed to couple it seems quite efficiently also out of the device, because that's one thing you have to worry about. You have an advanced mode, but can you actually couple it to something so that you just don't lose it somewhere at the interfaces? And so that seems to work better than expected. It could be that some of these for isolators that I also mentioned, that there could be some opportunities there. As I think we also talked about, trying to engineer a structure that absorbs very well by coupling it to an electronic degrees of freedom potentially. That would be interesting to look into, and that it was very much this idea that I also presented from Arno Reifenberg's group, where they use atoms as the absorber, as a dissipation that just scatters the photons out of the system. But that could be done in other manners as well, and I think that would be interesting to look at. Yeah, that's probably the best I can think of.
Thank you, Peter. We can discuss some other time.
Absolutely, yes.
There is another question from Nutachai Jutong. Are you there? We'll give you the microphone. You can go ahead and unmute your microphone and ask your question. Okay, it seems that he's not there. I think that there are some people coming in and out on the link on the meeting. We should probably close the tutorial at this moment and then go to this Zoom meeting so that you can have during the coffee break open discussions with Peter. You have the link in the email that was sent a few days back, but also you can find it directly on the Zoom chat. So you can click on there and they go to that link.
Okay, sure, we'll do that.
Okay. So it seems that, yeah, you should, yeah. So this is for Nutichai. Yes, go ahead and go to the other meeting to ask your questions there. Sorry about this. See ya.